All right, this will be chapter 2 on two-dimensional kinematic motion. All right, this will be motion either in the x direction, the y direction, or a combination of both. So we're going to look at what does this mean. We have a few quantities here. We have displacement, which we defined as delta x if we're in the x direction. Again, our coordinate system is y and x. And the only difference between these two is the fact that in the x direction, we have no natural acceleration other than what we do, but in the vertical direction, we have an acceleration of g, which is minus 9.8 meters per second squared. So we define up as positive, down is negative, to the right is positive, to the left is negative. Again, this will be just a short introductory video as far as that is concerned. All right, so we define that as delta x or delta y. Delta, it means change. We have velocity, which is defined as delta x over change in time. And this will be given by the Greek letter v, and this is in units of meters per second, for the most part. And then we'll have acceleration, which we define as delta change of velocity over change in time, which is a, which is in units of meters per second squared. So this is what we call that, as far as that's concerned. Now when we talk about velocity, we'll have velocity could be at a given moment, or generally defined velocity is average velocity is change in x over change in time. So as an example, if we go, say, 350 meters in 5 seconds, our velocity is 70 meters per second, our average velocity. Now, could be we're actually going faster and slower over the period of time, but the average is 70 meters per second. To give you an idea of what this is as far as how speed this is, a little bit on conversion. 1 meter per second is approximately 2.24 miles per hour. So 70 meters per second, so that would be 70 meters per second times 2.24 miles per hour per meter per second, which would be approximately, let's see, a quarter, 140, about 160 miles per hour. And sometimes conversion to English is useful because we understand English distances, unfortunately, better than metric distances. So that's what the average velocity would be. All right. Instantaneous velocity, on the other hand, is velocity at a given moment. Velocity at a given moment. Right? This could be like a speedometer. A speedometer is a perfect example of velocity or speed at a given moment. Say you drive down from here down to Minneapolis, about 200 miles, and it takes you 4 hours, right? So 200 miles divided by 4 hours is approximately 50 miles per hour. All right, but during that time, that's your average velocity. But during that time, you could be going stopped. You could be going as fast as 80 miles per hour, depending on where you are. That would be, the average would be this. The instantaneous, what you go is along the way. Okay. Moving along here a little bit. So if we do this as a graph, right, we'll be looking at graphs. We can do position versus time. And in this case, we have x versus t. The slope is the velocity, change of rise over run. And if we do a velocity versus time graph, which we'll see, then the slope of this is the acceleration, A. So we'll be using these as we go along. So if you have a graph such as this one, the slope is constant, so the velocity would be constant. If we had a graph like this of position versus time, and we do this, the instantaneous velocity is the slope of the line at any given moment, but the average would be where we start, where we finish, distance-wise, divided by the time. But we're not, this part of dealing with slope at a given moment is more for calculus, and that's beyond the scope of this course. All right, so just one last thing here. I'll just introduce that. We talked about acceleration already briefly. Now we have acceleration which is in units of meters per second squared. It's change in velocity, change time. Now, if going into the x and y direction, if I have an acceleration, say in this direction of, say, plus 5 meters per second squared, that means I'm accelerating in the plus direction 5 meters per second every second. Being negative does not mean that you are slowing down. All this is going this direction or that direction. If I went in this direction, minus 5 meters per second squared, I would be accelerating that way to the left at 5 meters per second. Where we see is acceleration, or where we see slowing down, is if you have velocity and acceleration opposite directions. So we'll see this. If we have a velocity, and we're going to use naught, a little letter there, for initial velocity. So what we start with, 15 meters per second, right? Plus 15. And then our acceleration is 5 meters per second squared. Right? Question would be, how far are we going after, say, time is 2 seconds. All right? We'll plot this, and I'll pick this up on next lecture. All right, so we'll plot t, 0, 1, 2 at velocity at, initially this would be 15 meters per second. Our acceleration is 5 meters per second squared. So after 1 second, we're increasing velocity about 5 meters per second. So this would be 15 plus 5 is 20 meters per second. And after 2 seconds, it would be another, it'd be 20 plus 5. Let me write this with our initial velocity. It'd be 15 plus 2 times 5 would be 25 meters per second. So how we can write, so that our velocity is increasing that way. We can write this as an expression is V naught plus A times T. So I will leave that there, because the question would be what would happen is if I have velocity this way, but an acceleration in the opposite direction. I'll pick that up in the next part.